So hello and welcome. In this presentation, we're going to look at part 3 of topic 4, where we consider a time delay system, which has a delay term in the output measurement vector. And what we like to do in here is we're going to do the decomposition. We're going to express the unknown input in its entirety. And so we're going to explore what are the conditions that allow us to be able to express the unknown input in its entirety. And we will show that we can express the unknown input in terms of generalized functional. So this is like an extension to our previous part, which is part 1, where we did not have CD, X, T minus tau in the output measurement vector. And in our development, what happened in here is matrix CD is of dimension P by N. We also assume that for simplicity in our presentation, matrix C is in the canonical form. And we pick the output measurement y1 of t. In other words, we call it y1 of t. That measurement going to be used for the realization of the unknown input, and we're going to use its first derivative. So accordingly, what we're going to do is we're going to partition matrix CD into two sub-matrices. The first one is a row matrix, which is basically associated with the output measurement yi of t. And here, yi of t, for simplicity, is basically the first output measurement. So that one is a row matrix, and the rest of the CD matrix is given by CDR. So that's where we see the dimension of CDI and CDR. Now, if we use our existing stack transformation from the previous topics, where we pick the metric T to be the E metric and D, and E has a specific structure, right? So we're not going to go into detail of that again, and assuming that this is a well discussed bit already. So when we apply this stack transformation into this time delay system, it is relatively straightforward. We obtain the following equations. Now that is basically the same as the previous expressions, where we got the first part of the equation x bar 1 of t. By the way, x bar 1 of t is of dimension n minus 1. That one is free of unknown input. The other equation is x bar 2 of t is related to the unknown input d of t, and that's where we can explicitly express it as were done in the previous topics. Now, the thing about of this matrix CD is that its presence in here further complicate the decomposition. So when we apply this transformation matrix T, which is E and D, we got this bit here, which is the well-known parts from previous decomposition. We also arrive at another term in here, and that linked to the delay stack vector. And so, as usual, if we go ahead with employing an invertible metric V with a specific structure like C times D and P, where P is of a particular structure, we're going to get two submatrices, V1, and V1 has a special form. Remember that? it has just one non-zero element in there, and that non-zero element corresponds to the first derivative of the output measurement y1 of t. Now the key thing in here, when we apply this matrix, we pre-multiply both sides of this equation by that matrix, we realize two equations. Right. Now, have a look at this equation. When we look at this equation, we then see that, wow, we are facing a little bit of a problem in here. The reason for that is because when we look at how to explicitly express x2 or x bar 2 of t in its entirety, we are having problem because we also have a delay bit in here. So one way to overcome that problem, which what we propose in our book, is to make this matrix, or this happen to be a scalar. All right. So what we're saying here is we need to impose a structure on matrix CD. Now remember, CD is the one that come into this output measurement. To be able to explicitly express x2 bar in terms of the output measurement y1 of t and the other stack vector x bar 1 of t, with the hope that when we do it, we put it into here, we can then realize a reduce the disturbance-free time delay system. That's the whole idea behind that. So when we actually face with this equation, we need to impose this structure. Okay. So we need to say, look, things are not that easy as at what we would have hoped for. When you have some complication in the output measurement, in other words, the output measurement is not only a combination of the stack instantaneous stack vector, but it's also a combination of the delay stack vector, which is most of the time might be the situation in a practical situation. The output measurement might be a combination of the instantaneous stack variable and also it delay stack variables and so on. So this is a more general situation. There, and then so in this situation, we have to impose this constraint there, okay? And of course, if this constraint is satisfied, then that term there is gone. It's gone. So we're left with an expression for x bar 2 of t in terms of y1 of t and this delay stack vector. Now, when we further look into this condition, we can see that the following two conditions, either one of them hold, will ensure that this condition hold. And that's where we look deeply into that expression. So one of the conditions is, what about if this thing equal to 0? And when we talk about 0, it's a 0 row matrix. Now, if it's 0, then 0 times D, which is a column matrix, then that will ensure that term is 0. So one condition is V1 times CD is 0. So that means that we impose a specific structure on the first row of matrix CD. Remember that V1 has a specific structure. It has a non-zero element in there, the first non-zero element. And the rest of the elements in V1, they are 0. And remember, CD is a row matrix of dimension P by N. So if we want to realize this condition, which we will come to discuss later on, that would mean that the first row of matrix CD, which means that this row matrix here has to be 0. And the rest of them, it can be anything. It doesn't matter. So there is a restriction on the entrance on the structure of matrix CD when we impose this structure. All right, and then the other bit, of course, is we want that term there 0. If we want this term is 0, what we need to do is we can impose this structure. So in other words, the first row of matrix CD is basically the null space of D. Okay, so CDI times D is 0. So in that case, we can then say, look, we don't need the first row of matrix CD entirely 0. It can be non-zero, but it has to be the left null space of D. In other words, it's multiplied by D is 0. So we're going to have two conditions. And either one of them will ensure that this is 0. So let's explore on these conditions. And by the way, the detailed discussion is in chapter 5 of our book. Okay, so let's explore this condition first. Now, when we have this condition, what does it mean? It means that that one is already 0, and therefore, when we multiply it to E matrix, it's also 0. That make the derivation of the non-input decomposition is a bit easy, because when that thing is 0, we also have that term there is 0 as well. So firstly, we impose this structure, and then secondly, we say that if V1 CD is 0, which is this condition here, then the other thing is also automatically equal to 0. So the two terms in here become 0. And we left with just a simple expression. That is a simplified form. We express x bar 2 of t in terms of y1 of t. And this is possible if this condition holds true and the first row of matrix CD is 0. Okay, the first row of CD, in other words, CDI is 0. So this is the first condition. And of course, when we substitute this x bar 2 of t back into this equation, we can easily obtain reduced orders disturbance-free time delay system. And that's exactly what happened in here. We plug it in and we substitute it in, we have this expression. And of course, when we substitute x bar V1 CD equal to 0 in here, and we also apply this condition in there, we also arrive at the output measurement. The output measurement y tilde t is this one here. That one there is V2y of t, and then have a look of this term in here. Have a look at this term in here. This term here is the delay of the output measurement, because y bar 2 t is this expression in there. So if we delay it, then we will get V1 y t minus tau. And then when we move this thing onto the left-hand side, we get two terms, V2y of t, take away V2 CDD x bar 2t minus tau. And that's where we call it y tilde, a new measurement vector. It's a new measurement vector. Before it was just V2t. We call it y bar of t. Yeah, y bar of t. Now it's y tilde. It's just another notation for it. This y tilde t is y bar of t and the delay of the output measurement. And of course, we know the output measurement yt, and then we can delay it. And therefore, we can realize y tilde t, which is an output measurement vector of the reduce or the time delay system. So we got that term in there. And then when we go back and look at the other terms, of course, this one is called C tilde 1, C tilde 1 x bar of t. And that's where we got this term in here. Now we also have an extra term in there, an extra term in our output measurement. And that extra term is linked to this expression here. All right, the link to this expression here. So we call that one another name. And remember, have a look here. It's actually linked to CD, the output matrix CD associated with the delay stack vector. So we call this whole thing here, whatever name it is, it's called C tilde D1. Now the thing about this reduced order system is it is a reduced order time delay system with no unknown input. However, the output measurement is no longer just contain an internal stack vector, but it also have a delay stack vector in there. So there we go. We got this reduced order system. The time delay system happen to have the delay vector in there as well, the output measurement here. And we have all these definition of all of those terms in there. And then, so once we substitute this expression back into the unknown input expression in here, and expression x bar 2 dot in terms of y1 dot and so on. So we're going to get this unknown input expressed in its entirety. Now, when we observing this unknown input, again, it's just a derivative of output measurement number 1, combination of the output measurement number 1, and delay. Actually, this is because V1 has a special structure. So this is basically containing Y1 of t. If we use Y1 of t as the preferred output measurement in the decomposition. What happened in here is actually that one. And then this is also another delay Y1 t minus tau. So when we look at this, that's no problem to realize the estimation of the unknown input. We also have this generalized functional. Have a look at that. Generalized functional. So to be able to estimate the unknown input asymptotically, then we need to design a generalized functional observer for this system here. And remember, this system itself is no longer just a simple time delay system. It has a delay term in the output measurement vector. So again, when we come across this kind of situation, this class of time delay system and this generalized functional, of course, we need to develop suitable methods for directly estimate this generalized functional for this time delay system. Okay. And that's why we have a lot of expository investigation into various aspects of it, and that's the reason for so many chapters in our book. All right, so that's where the first condition. This first condition gives us a similar time delay system compared to the other condition, which we're going to show later on. But it's still when you look at this, you got a time delay system with a delay term in the output measurement. And this output measurement vector is also of dimension p minus 1. It's also contain the instantaneous output measurement vector and the delay output measurement vector. Of course, we know y of t, so this can be easily obtained, and that's why this output measurement vector is known to the designer. The unknown input itself is in terms of a generalized function now. All right, so we go to the next condition, which is this condition in here. What we are telling is we can relax a little bit about the structure of CD. We don't need it to be or zero, the first row but to be zero, all of that. In fact, it can be non-zero, but it had to satisfy this nose by condition. Still a relaxation over this requirement. Okay, it's still a relaxation of that. Now, the price that we had to pay for is we're going to get a more complex reducer the time delay system. Everything in life has a price for it. So when we impose this structure, which is the first row of matrix CD, multiplied by the metric D has to be 0. In that situation, when we go back to this equation in here, we have this term 0. That's not a problem because we impose that structure in there. Now this term is 0, but this term here is not guaranteed to be 0. It's not guaranteed to be 0 because the first row of matrix CD can be non-zero, and therefore this term can be non-zero. So that's why when we express the unknown input, this stack variable x bar 2 of t, it will be in terms of this expression as well. Okay, that actually, by the way, that's what done in Howell and Muller. They didn't impose any structure on this, like V1CE. This is V1CDE now. Okay, anyway. So we get this expression, and it then just a matter of substitution. It's a little bit tedious to do, when you substitute this one back into this equation. And then you need to take some sort of differentiation of the when you take x bar to dot, then we also have that term in there. But that can be done. It's not a big issue at all, and we're going to skip the detailed derivation. It's just that we're going to leave it to the reader to verify this expression. We know it's 100% correct. So what happened in here is when we substitute this expression back into this equation, and after some rearranging, simplification, and so on, we arrive at and also when we substitute that into this equation, we also obtain an output measurement vector. So together, we obtain the following reduced order time delay system. Have a look at that. The one I circle in dark lines in here tells that not only we have a delay stack vector x bar 1 t minus tau, we also have a multiple delay in there. So you see that it's got a multiple delays compared to the other condition. We only have one delay stack vector in here. This is because the expression is simpler, because that term there is 0. That is the price to be paid for when we impose a more stringent condition. See that? So when we have this condition, we're going to have another delay term, delay stack vector term, which is a multiple of tau, which is 2 tau. And then the other bit is when we look at the measurement vector. Oh, there we go. We got another term in here, and we call them different notation and so on. And we have explicitly expressed and show how all these matrices are obtained, and they are given in here. For example, when we look at A tilde D11, hope that the notation is not that confusing. It is in terms of the submatrix of the delay of the matrix A bar D when we apply the stack transformation and we partition it into submatrices. So that one is known. This is also known. V1 is known. CD is known. E is known. So matrix A tilde D11 is known. And so are the rest of those matrices. Okay. So we see that it's actually in terms of that expression there. Because that expression is not zero anymore. It's not zero. Because of this constraint, which is a much more relaxed constraint than the other one. But that's the price that we had to pay for. So we got a reduced order time delay system with multiple time delays. And then the other bit is when we obtain an explicit expression for the unknown input, what we can see in here is it's all good in here. We got the first derivative of the output measurement, the output measurement y1, a delay of it, and a delay by 2 times. So all of that is no problem for us. And we also explicitly define what all these submatrices in here. So they are all known terms in this expression. Now, the thing that we like to stress in here, have a look at this. Have a look at this term, which is the linear combination of the reducer or the stack vector x bar 1 of t of that time delay system, which we have in here. Not only one delay term, we got two delays, and then we have three delays. Have a look at that. So what we have in here is a generalized functional. So you can see that the notion there, we could have many multiple of the delay stack vectors in there. And that's why we call it generalized functional. How to estimate this directly? Yeah, this is the important bit. How to estimate directly is the key to obtain a simplified structure for the unknown input observer. Okay, so we got generalized functionals, and therefore we need to design generalized functional observers for time delay system with both stacks and output vector. And that is the third part of our book. And that's where we will go into the next topic, topic 5, where we just show that, look, let's do some sort of a design generalized functional for some system, just to show the significance of it, just to show that this is hot off the press and we need to do something about it. Okay, and that is something very interesting. So let me recap of what's happening so far. We consider a time delay system with an output measurement vector depending on this delay stack vector. And then we look at the decomposition of the unknown input. By the way, we only consider an unknown input. Later on, we also consider multiple unknown inputs. But for the time being, it's just a single unknown input. And then by applying our metric decomposition technique, we arrive at this equations here. And when we're exploring these two equations, particularly the first one, we need to impose structure on matrix CD. Otherwise, we're not able to express x bar 2t in its entirety. Because it's got delay in there and all of that stuff. So we have to impose this structure in here. By the way, later on, when we go into another chapter in the book where we expand the dimension and all of that stuff, we can actually overcome that requirement. But in the meantime, if we stick to our metric decomposition technique using the way we've been doing, we impose this structure, okay? And then with this one, we have two conditions. One condition is much more restrictive than the other condition. Because it's restrictive, it leads to a much simpler reduced order time delay system with a delay term, a delay stack vector term in the output measurement. Okay, so that's the difference between this and the previous topic where we don't have it, we didn't have it. And output measurement vector, we didn't have this term in there. As you can see, it's all natural progression. We extend bit by bit by bit. That's why this book is an expository book. We set out to focus deeply into a particular research topic, and in doing so, we find out outcomes, results, and so on. And then so we we then obtain an unknown input, and this is again a generalized functional. So that tells us very clear that we need to estimate generalized functional for this time delay system. And the time delay system itself can be a simple or a complex time delay system. And here it's a bit more complex. It got this delay term in there. When we have the other condition, we get a more complex expression, and therefore we arrive at a reduced order system with multiple delays in the stack and the output measurement. This condition is less restrictive than the other condition, but the price to be paid for, we got a more complex time delay system. And then the unknown input is in its entirety involve generalized functional, which has multiple delays in there. So again, that reinforces why we need to develop generalized functional observers for time delay system. And very intriguing, in the next topic, we will show the advantage of design a generalized functional observer over just a normal functional observer. And we will see the significance of our development there. Okay, so thank you again. And this is basically real chapter 5 in the book. It's chapter 5 in here. So chapter 5 in the book, if you have time, please, when you go through it, you see that's the kind of development we had. We also got extensive illustrative numerical examples. At the moment, we are not showing the numerical example yet. We just show the decomposition, and the design of those functional will then be realized in the next discussion. So we then able to achieve the unknown input estimation for time delay system where the output matrix CD is non-zero. Okay, so in the next presentation where we're going to look at topic 5, because now it's timely for us to actually go and do it, because we demonstrated that we need to develop generalized functional. So please join me in the next presentation, in the next video, where we're going to design generalized functional observers for this class of time delay system. This is arrived from topic 4, part 1, where we didn't have a CD time delay term in the output measurement, and therefore we only have instantaneous stack vector combination of it in the output measurement y bar of t. But still, this is a new problem because we want to estimate directly. Okay, and it will be a very intriguing, interesting discussion because we will see that um, if we do the option one, where we say, okay, in order to realize a delay stack, realize an estimation of a delay stack variable, if we pick option one, where we design a stack observer for that term instantaneously and then delay it, it doesn't work. It doesn't work. But if we do estimate that delay stack variable directly, in that case, which means that this term here is chosen accordingly, then we estimate this directly. It works. Okay, so and then there are many more significant advantages that we will demonstrate in topic 5. Okay, we will demonstrate in topic 5. We will talk about how to design generalized functional observer first, and then we're going to take many examples to demonstrate that, to convince everyone that this is the way to go. Okay, so thank you very much for watching, and I hope to see you again in the next video, where we're going to jump into topic 5. We're going to consider design of this generalized functional for this system. Okay, so thank you very much, and bye bye for now. I see you again.